the session, who is Fabian Furra, and he's going to talk about reverse reconciliation, continuous variable quantum key distribution based on the uncertainty principle. Please.
Thank you very much for your introduction. So is the microphone working? Okay. I will talk about more theoretical part of continuous variable quantum key distribution. So what I will present is a new kind of improvement about security proofs in the finite size regime against coherent attacks. So I will just first give some introduction about security proofs for continuous variable systems. Then I will describe you the particular QKD protocol. I'm going to analyze and then show you QCrypt basic proof ideas. And at the end, discuss the optimality. So I don't think I have to explain what's QKD, but we have these three parties usually. We have Alice and Bob. They want to generate a key that is not known to an eavesdropper Eve. And what's important here is, of course, especially now, as we go more to kind of like technological standards and commercialization, that we have practical security analysis for actually specific implementations of QKD systems. And this is what I'm going to talk about. So there's different implementation we have heard. So we have discrete variable protocols. But what I'm talking here is continuous variable protocols. And I'm really grateful for the nice tutorial this morning that I actually can skip a lot of these things here. So these continuous variable protocols are usually based on encoding in amplitude and phase modulations. Then one produces Gaussian states. And these Gaussian states are then measured with homodyne detection. So what I'm particularly considering here is Gaussian modulation protocols, where the displacements of phase and amplitude is given according to a Gaussian distribution. So this QKD systems are much easier to analyze from the perspective of security. So there are some pros and cons of this kind of technique. So it's a cheap, homodyne detection, as we heard, is very cheap, efficient kind of technique to measure amplitude and phase, and also kind of like maybe there is a better or easier integration into current networks. But on the other side, it's like error correction is really, difficult, or is more difficult, because one has Gaussian distributed variables. And also the security proofs are more involved. So we didn't reach the standard that we know for discrete variable protocols. So, and another thing is that we often limited due to losses. And the fact is, like, as we heard this morning, is that there was this 3 dB limit that has been overcome then now by using reverse reconciliation protocols. So in a QKD protocol, and we have this quantum phase here where one has some quantum communication and one actually forms some raw keys. And reverse reconciliation means that actually Bob is sent in the error correction phase. Bob sends information to Alice, and Alice actually guesses Bob's raw key. This is in contrast to direct reconciliation, what is usually used for discrete variable. And with that, we can actually theoretically overcome this problem, and we can actually allow for an arbitrary amount of losses. So about security proofs in CVQKD. So of course, the security is usually as strong as the assumptions. And what I want to focus here, we have assumptions on the implementation. So we usually have some model to model the physical devices used in the protocol. And of course, they are usually not as accurate as they have to be, so there is implementation flaws or implementation loopholes. What I want to more consider is information theoretical assumptions. These are assumptions on the attacks or the finite size effects and so on. And especially what I want to talk is about assumption on attacks, because this was actually previously a lot of security proofs actually only cover certain kinds of attacks. And then what's kind of most commonly used is collective attacks. And such collective attacks are as follows. So like Eve can only attack each signal independently and always in the identical way. And opposed to that is, of course, we have these coherent attacks. Coherent attacks are just the normal general attacks where we don't have any restriction on that. And of course, the range of attacks here are usually much larger than here. And another kind of theoretical or information theoretical assumption one often does is that one assumes an infinite number of communication rounds. And this really simplifies the analysis tremendously. So if you have, first of all, what one knows is that coherent attacks actually collapse, and they're not stronger than collective attacks. So all this is like these possibilities to coherently attack all signals. I mean, arbitrary is the same. I mean, doesn't give you any, advantage than acting on each signal independently and identically. So, and also, a really nice result is that actually this optimality of Gaussian attacks. So that Gaussian collective attacks are the same, are like the strongest among all collective attacks. So this means that we have only to actually guarantee security against Gaussian collective attacks, and this is really kind of a small set of attacks, and this makes it possible to actually do then security proofs. Other simplification comes because we don't have to do finite statistics, and we also have to only consider this mutual information in this asymptotic limit. But of course, this is not practical. In general, in practical implementation, we have only a finite number of communication around, so we have to consider these finite size effects eventually. So with that, as I said, I mean, we have to guarantee composable security. We have seen this nice tutorial by Renato on yesterday morning, so that we actually that we can combine these different steps or these different subroutines in cryptographic protocols. And this usually, I mean, requires to consider different entropic measures. I mean, one has replaced mutual information or von Neumann entropy-based measures by smooth mean entropy measures. So, and that's recently, I mean, shown like some results about, I mean, coherent state protocols here, like they're proven to be actually secure against Gaussian collective attacks. And especially I want to emphasize is that in the next talk, this Gaussian collective attacks, I mean, this is basically just, we can translate this here directly to the finite key regime. But now, actually, Le Verrier did, I mean, what Le Verrier is talking in the next talk is that we can actually drop this Gaussian here, that we have actually prove against collective attacks in general. So what I'm focusing here is now coherent attacks. So there's basically two techniques at the moment. The one is based on some symmetrization of in the phase space, plus then post-selection technique, which is kind of borrowed from the discrete variable case, but doesn't directly apply to continuous variable. This is usually, I mean, Le Verrier and coworker had this really nice result, but so far they don't scale very well in the number of rounds. So they're not so feasible at the moment. Another attempt was actually using entropic uncertainty principle with quantum memory. So what we did there is that we actually showed, like for the first time, a security proof for a continuous variable protocol against coherent attacks. But what we need here is like, while this can be done with coherent state protocols, we need a squeeze state protocol using these EPR states. And what we also had, we had only done this for direct reconciliation protocols. And I want to advertise here this work, where we recently just with experimentalists in Hanover implemented the whole protocol, and also with the Austrian Institute of Technology, who was involved in the error correction. So please go to the poster 65 and 74 today, and here they explain the whole setup. So, but as I said, this has only been done for direct reconciliation protocols, and that's much easier. And we couldn't right away apply it to reverse reconciliation. But what I'm showing here is how we actually overcome these problems here to actually get, a security proof for reverse reconciliation, improve the distance. So this is what is going to talk about in the following. So the protocol is still a squeeze state protocol using this EPR state introduced in the morning. Both apply just randomly amplitude and phase measurement, and they repeat this many times. And this was actually the same step as in the direct reconciliation protocol, but the new step is now that we have some threshold test that has to, performed by Bob. And the threshold test is needed in order to actually guarantee that large measurements of amplitude and phase occur only with a really low probability. So and this goes as follows. So we have a threshold here. We want to bound that measurements above m, or with magnitude bigger than m are really small. And for that, we're taking the incoming signal. We reflect a really tiny part, so the transmittance is basically 1. And on this reflected part, we do just a heterodyne detection, so we measure amplitude and phase. And condition that this absolute value of these outcomes are small in alpha, we say the test is passed. And what I will show later is that this actually implies that the probability to measure here an amplitude bigger than can be bounded. So this is actually a new part of the protocol. So then in the classical phase, that just follows actually similar post-processing as in direct reconciliation version. So when Alice and Bob just publicly announced their choices for the measurement, and then they discretize the outcome. So we have here this m, here this is this threshold from before, and within this threshold we just use a constant binning. The parameter estimation here, the only thing what you have to estimate is actually the difference of these outcome strings here. So we have like the measurement and for that we use the phase measurements. And then we just take this average distance over all phase measurements. Or the shifted phase measurements, of course. I mean, the one we have correlations. And we also, I mean, for this protocol, we also need some variances of other things that I want to skip here. And then we just use the amplitude measurements to extract the key by doing reverse reconciliation and 2 universal hash. So this is the protocol, and the main result is here, this bound on the secure key length. So this is actually holds up against coherent attacks, is actually in the framework of composable security and actually considers all finite size effects. So this n here is just the number of amplitude measurements. This C over delta is the overlap of Bob's phase and amplitude measurements. Here is the correlation part. This is from the parameter estimation, and this gives us kind of like the statistical uncertainty, for the finite size statistics. And here we have just the bits communicated in the reconciliation protocol, and these are some terms that just logarithmic in the security parameters. So the assumption what's goes in, which is always really important to mention here, is actually only here in this part, in this overlap of Bob's phase and amplitude measurement. So here we assume now that we have, in the following, that we have ideal phase and amplitude measurements. And for that we have we have these implementation assumptions. First of all, that sequential measurements are independent, and especially strong is that we have to trust this local oscillator. But one can actually take here a more sophisticated model and incorporate some measurement or some implementation or more sophisticated implementation model. Okay, here is some key rates. So I plot here the key rate, which is just the length per transmitted quantum signal. Here is n equal to 10 to the 9, and the security parameter is 10 to the minus 9. So we use, these are plotted for a source which has been implemented in the lab and for different reverse reconciliation efficiencies. So here, actually, recently there has been a lot of kind of improvement. So this is here, this one work I said for the direct reconciliation protocol, we improved actually some efficiencies, and also the recent work here by Paul Chouguet and co-worker, where they actually got efficiencies which are compatible with what is assumed here. And for the energy test, so here are the parameters, discretization is 0.1. So we have a little bit of large alphabet, but this can be used using in the classical, the post-processing. So we can actually get rid of this problem, because this is artificial. The only maybe a few bits carry information. Okay, and what we see is that we actually get now distances above like 10 kilometers, so we get up to like 15, 16 kilometers if we have really good reconciliation. And it's also interesting, of course, for instance, if one thinks about satellite communication, as we have seen, in there the losses are much less, so we can actually go to much further distances. Okay, let me go now quickly to the security proof. So how do we prove that this is actually secure against coherent attacks? What we use is this entropic uncertainty principle with quantum memories. And this just means like the normal entropic principle means like that the entropy of this amplitude measurement and plus the entropy of the phase measurement, they are bounded by some overlap constant. So now we can extend it and say that the same holds if we include like this side information here in the quantum memory of Eve, plus the side information for the phase measurement in the quantum memory of Alice. And the good thing is that we can express this with the right entropy measure for composable security in QKD, and then we can bound this one by just looking at this overlap constant, and here the correlation only depends on Bob's measurement outcome and Alice's, quantum system. So you can actually, we have tool to bound this quantity here. But important here is that we have entire range. So that we actually have to consider here the entire range of the real line, basically. If we model that, because otherwise we can always overcome this uncertainty principle by just kind of like squeezing it in an area above a threshold. So we actually, it's really important, we only have an uncertainty here when we consider the real line. And this actually made some problem, and this had to be overcome by using this threshold test here. And this is then part of the statistical estimation, and the statistical estimation goes as follows. So we take, in the cases where we actually did a phase measurement, so this is kind of a random sample because we chose this randomly according to just a prefix distribution. So we have here a random sample, and of this random sample we can actually have compute this value here. And then what we have to do is we have to use this value here to actually kind of estimate how this average distance looks like on the key sample that we didn't actually measure. And in order to do these things, these are standard techniques from kind of statistical, from statistics. But what one usually has to assume is that the range of these variables here are finite. So if they're not finite, then we actually can basically say nothing about it. So we have to actually bring this to introduce this finiteness for these variables. And for that we use this threshold test here. And what we showed is that if this threshold test passed, so meaning that these outcomes here are smaller than alpha, the absolute value, that we can bound the probability to measure here on this outcoming part of the signal where we do then Bob's doing amplitude and phase measurements, that the amplitude and phase measurement is smaller than m is actually, bounded by this, or decays exponentially in this distance here. So the idea is pretty simple. It's just like, here is a phase-space picture, so assume that the incoming state here has actually large parts which have, which gives you a contribution around m. Then if we actually just take a little portion of it here by using this beam splitter, we can still actually, if the gap is long enough here, see if we actually are above this alpha. But for that, we actually have to take a really large m here, because this actually is approximately 1, and this has to actually compare with this alpha here. So, and this for the key rates we saw before, the m was actually to 10 to the 4, and this alpha is actually then now chosen to around 28 in units of h bar equal to 2. So there is actually a really huge gap. And this also this large m here causes some trouble in the statistical estimation, especially in the finite size regime, because this means that our statistical uncertainty are only decay really slowly. But there's a way how we overcome this problem is, by using kind of like a two-step procedure, because what we do first is actually looking at the variance of this average distance and estimate first the variance by using the variance of the phase measurements. Then using the variance of this distance, we can actually use some statistical tools to estimate the key. And in fact, this actually improves it tremendously, especially if we have a really large alphabet. here if this m is really large. And then we just can plug it into the uncertainty relation. We can bound this one, and we get a bound on the mean entropy, so on the information Eve has about the key. So this is the security proof. So let me now say something about the optimality. To me? Okay. So here important what you want to see is that here is this blue one is the finite key rate for reverse reconciliation. And the asymptotic rate here is the green one here. I mean, also for using entropic uncertainty principle. And this red one is the optimal one. So the important thing is that we have these finite size effects, but we also have that we can only allow a fixed amount of losses using this entropic uncertainty principle. So this is actually a real limitation, a fundamental limitation for using this proof technique. So let me skip this one and conclude quickly. So as I showed you, we have a new security proof against coherent attacks. I mean, in the finite size regimes, there's some experimental implementation, so it's actually feasible. I showed you this threshold test that allows us to deal with this unbounded measurement range, and maybe this also applies to some kind of detector range problems. And also, what's important here is actually that this entropic uncertainty relation is actually, this gives us a limitation, and we actually need different tools to overcome this problem. So if then I'd like to thank for your attention.
About going further and further works, do you think your way to estimate Hmax, I mean, it is the stuff which kills your protocol at relatively, I mean, not long enough distance to my taste, but with a good proof. Do you think there are other ways to have a tighter estimation of Hmax, or you think that?
I mean, the problem is not the estimation of this of Hmax here. Oh, sorry. Of this one here, the problem is the untightness of the uncertainty relation here. So, and of course I believe there is ways to overcome it, but it's not possible, or at the moment we don't know how it's possible by using actually the uncertainty principle, which works so really well for discrete variable systems, because there we don't have this problem of this non-tight.
I'm surprised because I mean, that you say that it's on the tightness, because the previous proof, which don't go as far, I mean, use the uncertainty principle, but for Shannon entropy and the smooth entropy are supposed to go close to them and in the asymptotic limit.
But I think you mentioned a different way how to use this uncertainty principle. Because this was a result in 2004-5. Yeah, but actually this wasn't based on the uncertainty principle with these quantum memories. This was a different bound techniques there.